Welcome back. And so, what's next up? Of course, with binary compounds where you have two different elements, you have to worry about, oh, we have orbitals of different energies that are mixing together with in maybe non-obvious ways. And so the band structures get a little bit complex for ionic compounds or intermetallic compounds, things like that. So this shows the kind of the derivation of band structure for manganese phosphide, so MnP. Right, and you have the phosphorus p bands and the s orbital, p orbital, the manganese d orbital, manganese s orbital, and they mix together, and you get basically a separated phosphorus s band, phosphorus p band, and a manganese d band. Right, they actually kind of stay separated, and this way of presenting band diagrams is a little bit different than what I showed you before, right? So here we have the p band, the phosphorus s band, the phosphorus p band, and the phosphorus d band. The phosphorus d band spans this whole thing, and it's only partially filled because manganese has 5 d electrons. Well, actually, in this case, it only has 3 because it's manganese 3 plus. And so that's a partially filled band. You'd expect this to be a conductor to some extent. Well, what is this stuff over here showing? Well, the important part is this part over here, labeled DOS. This stands for density of states. So remember how I said that, you get the energy levels really close together and they're kind of all overlapping? Well, this actually presents, this density of states part actually presents kind of how densely packed those energy levels are, because they're not actually evenly spread throughout one of these bands over here, right? So what this shows is that for this band, the energy levels are actually kind of sparse down on the bottom, but then towards the top, they're very tightly packed together, right? So density of states, the number or density of or how closely spaced the energy levels are, is kind of the x-axis over here in this density of states part, right? So here, it's not very far out on the x-axis. That means that those energy states are kind of sparse. And then where it's sticking out farther, that means that they're packed together a lot. Why is that important? Well, for the filled bands, it's not that important. But for the partially filled bands, this actually will determine things like how conductive a metal is, right? So if we look right here, this is where you have the HOMO and the LUMO. So those are the energy states that are going to be responsible for the majority of the conduction. And so if we go across and look where that shows up on the density of states, it's right here, right? And so in terms of density of states, that's actually at kind of a low point in this diagram, right? Right below it, we have high density of states. Right where that HOMO and LUMO is kind of at this trough. And so that means that they're actually kind of spaced out a little bit here, more than they would be here. And so that means that we'd expect a lower conductivity than if the Fermi level had, or the HOMO-LUMO had been right here. Right, so this is, I don't think this is actually covered in the textbook because it's kind of an advanced concept, but I thought it was important to actually bring it up. So let's look at some terminology, right? So here we have the band structure for a typical semiconductor. And so for a typical semiconductor, you have a filled band and then an empty band, and in between, there's a space. Right? So this doesn't conduct electricity very well because the electrons in the HOMO don't have any LUMO levels that are really close to them. The electrons here would have to go all the way up here to get to be able to move around. Right? Well, the energy distance between here is called the band gap. Right? So this the distance here represents a difference in energy between the HOMO and the LUMO, and in solid state materials, that's called the band gap. Right? So for metals, there's no band gap. For semiconductors, there is a moderately sized band gap. And for insulators, there's a large band gap. Insulators, you can't promote the electrons up high enough, at least with thermal energy. You can do it other ways. Some other terminology, and I slipped a couple times. It turns out that solid state chemists and material scientists use a different term for the HOMO when applying to solid state materials. They call it the Fermi level, but the Fermi level is the same thing as the HOMO. It's the highest occupied orbital. It's the highest energy electrons that are in these bands, right? And then we have the valence band, which is the lower energy band that's filled, and then the conduction band, which usually is an empty band, right? And so that's the terminology of these semiconductors. A valence band, a conduction band, a band gap, and a Fermi level. So the band gap is the energy between the valence and the conduction, between the filled and the unfilled. Right, so this chart, again, this is not in the textbook, but it's a really useful chart for a couple of reasons, right? So this lists a bunch of different some ionic compounds and some ionic compounds that are semiconductors, some that are insulators, and then some solid materials that are semiconductors as well, right? So we see sodium chloride up here. It's an insulator. This axis is the energy of the gap. So this is really the band gap. So sodium chloride has a band gap, 750 kilojoules per mole. That's a giant band gap. Lithium iodide, lower band gap, but it's still considered an insulator. Sodium chloride, that's pretty much an insulator, but it's getting down to the region where it might be accessible, that band gap might be accessible to thermal electrons. And then down here, these really start to be considered semiconductors are right around here and then down below, right? So silicon is the classic semiconductor. There are also compounds like gallium arsenide that are right around that energy, and so they also form really nice semiconductors, cadmium telluride, stuff like that. And then down below, some things like tin. Right, so this is useful for a couple reasons. One is that it has a lot of different combinations. So if you want to know what a band gap is for a particular material, you can look on this chart and just read across to this axis. Well, the other thing that this way that you can use this is the x-axis is based actually on this chi. Remember, chi stands for electronegativity. So for these binary compounds, gallium arsenide, you can put the electronegativity of gallium in here at times 10, minus 17.5, and take the square root, and then add that to 10 times the electronegativity of the other compound, minus 17.5, take the square root of that. Add them up. And if you do that for any combination, and then go straight up from the number you get and across, you can predict what the band gap would be for that material. Right? So even if it's not on this chart, if you know what the elements are, you put in the electronegativities to this equation, read up and then across, you can estimate a band gap, right? And so this is, plotting a whole bunch of compounds, and it looks like it's a pretty good correlation, right? You're not going to get completely on for every single thing, right? So for the gallium nitride, the actual band gap is around 310. And if you went up to the correlation line and went across, it would be about 325. Right? So that's actually pretty close, not too bad. And none of these compounds are very far off this line. Again, empirical correlations are really powerful tools, but you have to go through the work of actually measuring a whole bunch of things and then finding the property that actually correlates well with what you're looking at. So I want to mention you can actually tailor band gaps by picking different combinations of materials. And so this is a graph showing on the x-axis gallium and then a mixture of phosphorus and arsenic. And if you look at a periodic table, you'll see that phosphorus and arsenic are in the same column on the periodic table. And one of the keys to doing this is that you have to maintain the same number of electrons, right? You have to have two elements that have the same number of valence electrons. And so phosphorus and arsenic have the same number of valence electrons. You also have to have two things that are not drastically different in size, right? So these are kind of right next to each other, top and bottom. And so this x-axis says, okay, x is 0 over here, and x is 1 over here. So when x is 0, we have 0 phosphorus and 1 arsenic. So it's gallium arsenide over here. What about over here? Over here, x is 1, so it's gallium phosphide over here, and there's 0 arsenic. In the middle, 0.5, you have 0.5 phosphorus, 0.5 arsenic, and so it's a 50-50 mixture of phosphorus and arsenic that's just kind of mixed together in the lattice, right? And so you make this material, and you expect that since the chemistry of phosphorus and arsenic are approximately the same, you'd expect the same lattice of gallium with both of these. Sometimes that works out, sometimes it doesn't. And so the phosphorus and arsenic just kind of take random spots in the lattice. So this x-axis is basically how phosphorus rich it is over here, how gallium or arsenic rich it is over there. Now, what about the y-axis? Well, this y-axis is the length of the unit cell, and that's the black dots. And you see that, oh, when it's all arsenic, you have a large unit cell. When it's all phosphorus, you have a small unit cell. Not a big surprise, since phosphorus is smaller than arsenic. You'd expect that as you add more phosphorus, it would shrink down. What happens to the band gap? Well, the band gap isn't a straight line. This is actual experimental data that's plotted, but it starts over here, right? So this axis is the band gap. It starts at 1.4 for the arsenic one, and it jumps all the way up to a little bit over 2.2 for the phosphorus one, right? And so you can tailor whatever band gap you want by choosing the correct ratio of phosphorus and arsenic. Now, it turns out this is going to be important when you talk in class about, we're going to talk in class about making diode lasers, right? You can use this technology to make diode lasers. It turns out the color that you get depends on the band gap. And so by using these mixtures, you can tailor the band gap to any energy you want, meaning energy, any color of light that you want. Pretty cool stuff. Okay, so the last thing I want to talk about is a concept called, actually, maybe I'll stop this and we'll do